Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step on inside as we jump into the Chapter 6 review in the Big Ideas Math Integrated Math 3 textbook. This is all things rational functions, beginning with inverse variation, then we graph rational functions. These are in order. 6.3 was multiplying and dividing rational expressions, 6.4 was adding and subtracting them, 6.5 was solving rational equations. So 6.3 to 6.5 I feel like is a very big meat and potatoes version of what we do algebraically. 6.2 what we do graphically, and 6.1 it fits in the chapter, but it kind of seems a little bit off kilter from the other ones. Nevertheless, we will review them all. 31 questions in total. I got the PDFs down below for both this problem set of 3 pages as well as graph paper, because we are going to be graphing, and timestamps for each individual problem in the beginning of each section. Without further ado, I'm going to go ahead and get started. We are going to look at inverse variation on section 6.1. This is the opposite of direct variation. You can see a general form of inverse variation right here. Direct variation would be y equals a times x, and there are other variations of these that we've seen as well. Again, this is direct variation. I'm doing this with my mouse, I apologize. Direct variation is here, inverse variation. A is the constant of variation for either of these. So it's a constant, it's unchanging, it's a number. When we divide y by x, we have direct variation with a constant. When we multiply x and y and we have a constant, we have inverse variation. The variables x and y vary inversely, and y equals 12 when x equals 3. Write an equation that relates x and y, then find y when x equals negative 4. Very basic approach to everything. Once you know that it's inverse variation, you set up the scenario, you substitute those two values, 12 for y, 3 for x, and solve for a. That a will be used constantly for any such values in this variation. When x is 2, y is this. When x is 3, y is this, etc. When x is negative 4, y is negative 9, and that's part of the inverse variation. Now, we've also graphed things like this. You probably know what the graph now looks like these days and why that is, and I hope that's a good kind of take-home thing for us. Now, numbers, this is a lot of inverse variation questions. We have 10 of them, and there are only 31 questions total. I feel like this is a little front-loaded. Nevertheless, we're still going to be doing them. They'll go pretty fast, actually. Numbers 1 through 6, whether 1 through 4 in equations or 5 through 6 in tables, we are stating whether x and y show direct variation, inverse variation, or neither. Now, number 1 shows a product of x times y equals 5. I did mention that if you multiply, it's not this one, if you multiply your two variables times x on both sides right here, you would get inverse variation. If you want to know for sure, divide both sides by x, and you can see you're dividing some a by x, therefore this is inverse variation. Number 2 says 5y equals 6x. This is one of those things where just keep getting y by itself on each of these and tell the audience, I'm telling you guys, tell the world, tell everybody what it is that you see here. If I divide by 5 to get y by itself, 6 divides by 5, so does the x, but let's see what's multiplying by x, some constant of variation. It's an a times x. This would be an example of direct variation. See, the inverse and direct variation, I want to talk about this when we hit the tables. Direct variation is as x goes up, y goes up. Inverse variation is as x goes up, y goes down. Not all forms of it, just because something goes up, x and y both go up doesn't make it direct variation, but that's the only case for which direct variation can apply, and this is an example of that. As x increases, so will y. Number 13 has a quotient of x and y together, but if I got y by itself, and this requires kind of switching the places of y and 15, multiply both sides by y, divide both sides by 15, you get x over 15. Now, does x over 15 mean it's inverse variation because there's division on this side? Not quite. X is not in the denominator of its equation. It's in the numerator. So a better rewrite of this, in fact, would be instead of saying dividing by 15, say it's multiplying by 1/15. And I shouldn't box that, though. And that would be direct variation once again. It's some a times x. Y may not be going up as much as x is. Doesn't mean it's not direct variation. And that being said, I did mention that when you divide your two variables and get a constant, it is direct variation as well. It doesn't matter if I divide x and y and get the constant or y and x and get the constant. The point is, it's a constant. And that's what we have. Number 4, let's get y by itself by adding 3 to both sides. We have y minus 3 equals 2x. So when adding 3, we get y equals 2x plus 3. It's a linear equation. It's not direct variation. This would be direct variation. Y equals 2x. Part of direct variation also includes that when x is 0, y is 0. There is direct proportionality from one to the other. But when x is 0 here, y is 3. This is just a linear equation. This is in neither case. So as I said, just because x goes up, y goes up doesn't make it direct. Just because x goes up, y goes down doesn't make it inverse. Inverse variation. All right, numbers 5 and 6 are a little more of a copy-paste job for me when it comes to the comparisons. What we're going to do is either multiply y with x and see if we have a constant, or we will divide y with x and see if we have a constant. In other words, check for inverse or direct variation based off those constants. Now, I'm only going to bother testing the one that seems to make sense with the information. Because x is going up and y is going up, the only possibility is if this is direct variation. So I'm only going to test dividing, say, y with x. So y over x here, and if I have a constant y over x each time, then it's direct. If the constant breaks, then it's neither. 35 divided by 7 is 5. 55 divided by 11 is 5. 75 over 15 is 5. And 100 over 20 is 5. Because all of these are constant for this thing, it's direct variation. And in being direct variation, that's also the constant of variation you're looking at. This equation could be written as, which they're not asking us to, not yet at least. We have a lot of problems to do this with. This would be y equals 5x. Y is 5 times that of x. Number 6, I've had a lot of direct lately. Let's pray on an inverse. Or, I guess, a neither. Let's see. On number 6... x is increasing and y is decreasing. The only candidate here is inverse variation, which means testing the product of x and y. I have no reason to test y divided by x. That's not going to work. So clearly, that's not going to be a constant. But x times y we can get a check on. I'm going to start with 4 times 8. I got 32. I know 10 times 3.2 is 32. Let's see if the others pan out. 20 times 1.6 is the same as 16 times 2, which is 32. And 6.4 times 5 is the same as 64 times divided by 2, 64 times 0.5, and that's also 32. So these are all constants. You can use the calculator if you have to, but the point is the product is constant. That's actually a case for inverse variation. Means you can divide, say, 32 by x, and you'll get your y value. 32 divided by 5 is 6.4. 32 divided by 8 is 4. Things like that, you have inverse variation on that. A lot of inverse variation with this whole thing. I mean, just, again, a third of the problems pretty much are inverse variation. That actually is the first surprise for me. Numbers 7 through 10 are like the example up top. The variables x and y vary inversely. No more direct variation. It's all inverse from here. It's all using y equals a over x. Use the given values to write an equation relating x and y. For example, x equals 1, y equals 5. We will substitute y equals a over x and then solve for a. Clearly, 5 times 1 is 5. And a divided by 1 is a. And then we can make our equation y equals 5 over x. This is our inverse variation equation for this situation where this holds true. And then we got to figure out what holds true for the rest of it. It says, find y when x equals negative 3. So y equals 5 over negative 3. And I mean, that's negative 5/3. I have no other way to write that. Y equals negative 5/3 when x is negative 3. That's number 7. These continue, and they continue in short order. We've done them several times, not only in the section, but also in the quiz review, and now we get to do it several times here. So pardon me if I go rather quickly through this set. Negative 6 equals a over negative 4 is the next set here. We'll multiply both sides by negative 4 to get positive 24. It is a positive value. So the equation is going to be y equals 24 over x. See, dividing by a negative gave us a negative, and therefore dividing by negative 3 will also give us a negative value. In this case, it's going to be negative 8. Number 9. They try and get a little tricky now. They deal with fractions. And of course, this is a rational functions chapter. So it's not completely out of the realm that we deal with something on fractions. Let's see how this one works. Tricky, tricky. It says y equals a over x. Now, how do we divide by 5 halves? One way is, well, listen, there are a lot of different things that we can say on this how you want to. You could multiply, literally, let's multiply by 5 halves right now, boom, boom, and that's a way we can solve it, right? The whole idea is we got to get a by itself anyway. What's wrong with just saying times 5 halves right now, and it will cancel out. Okay, nothing wrong with that. So this would be a equals, now 18 divided by 2 is 9, 9 times 5 is 45, and that would be the a value. What are other ways you can think about it? 5 halves is also 2.5, so you can multiply both sides by 2.5 to do the same effect if you're just confused on the fraction. The third way that I want to bring it up, though, after I just say times 2.5, you should get 45. The third way I want to bring up, though, is something we're going to have to do later anyway, which is dividing by 5 halves is also multiplying by 2/5, which means, you know, you can multiply by 5 halves the reciprocal to get this by itself once again, but you can also see this as 18 equals 2a over 5. If anything here helps you, you can write it as a proportion and do cross multiplication. A lot of different ways you can get that by itself. I don't know why I'm sticking on the fraction portion of that. I just want to remind you that dividing a fraction is multiplying by the reciprocal, something we'll use later. But in proportions, you can cross multiply. These are things that we touch on in section 6.3 and 6.5 and things like that. But anyway, we got a is 45. That's the value you'll get no matter what you do here. So our equation is y equals 45 over x. It just so happens that we divided the wrong number to get something kind of crazy there. We were dividing 5 halves, keep in mind. Okay, so here is our equation. Now we're going to substitute -3 for x. I said, pardon me if I go quickly on these problems, and suddenly I went significantly more slowly than any other problem I could have done. Number 10, probably to the same effect. There's a fraction here, and it's on y this time. We have x equals -12 and y equals 2/3. Now in this case, y equals a over x. This is truly a proportion this time. This is one where maybe cross multiplication is the best thing for you. You can cross multiply the 3 up there, or you can just multiply both sides by -12. So let me give you two options. One is cross multiplication, and then you divide by 3. Or the other is just multiply both sides by -12 outright, because the goal is to get a by itself, right? This does it. So this would be a is 2/3 of -12. -12 divided by 3 is -4 times 2 is -8. No matter what you do, you get it. Getting you feeling comfortable with fractions in the way that you so prefer. So our equation will be y equals -8 over x. Now we are going to divide -8 by -3. And negative over negative is a positive, so you get positive 8/3. And a fraction's fine. We had that for number 7 as well. Okay, there are our inverse variation questions. No word problem ones even, but that's all we got. All right, let's go into section 6.2 on graphing rational functions. We have 3 problems to do there, but before so, let's take a look at the one that they give us. They graph y equals 2x plus 5 over x minus 1 and state the domain and range. We have the same instructions, by the way, down here, so get ready for that. This one is a little bit different looking than the first 2 sets of problems, though, because this has a binomial divided by a binomial. That's kind of like this third problem, so get ready to talk about it then when we hit it. They're going to start by drawing asymptotes. Now, this form that they have is not our transform. It's not our general form that has the HK, the AHK stuff. This is H. It's x minus h, x minus 1. So x equals 1 is our vertical asymptote. It's the value of x when we divide by 0, which is undefined. That's why we have a vertical asymptote there. No points there. And then the horizontal asymptote, we talked about it at the time, but basically you divide your linear coefficients. Because these are the same degree, top and bottom, we get to divide 2 by 1 and get 2. We'll see other ways that we can actually get to this. I'm actually going to write it, in fact. So we graph those, the vertical asymptote at x equals 1, horizontal asymptote at y equals 2. Notice this graph is scaling by 2s, if you can see it. Then they start just plotting points in general. This is something I don't generally do. I tend to actually find the x and y intercepts. Find the x-intercept by setting y equal, the numerator equal to 0. So here I can do the following. I can do, give me a second. So for the x-intercept, I can do 2x plus 5 and set that equal to 0. Subtract 5 divided by 2, you get -5 halves. That's -2.5. So if you can tell, there is probably a point. If there's -2, -1/3, here's probably -2.5, comma 0. So that's the x-intercept. The y-intercept, you set x equal to 0. This one's pretty easy for these equations because 2 times 0 is 0, x is 0. And then you just get 5 over -1, which is -5. So you get a y-intercept of -5, and that's actually one of the points they have there, and an x-intercept right here as well. 2 points you can plot. These points can also reflect on the other side depending on how far these things go over, things like that. For example, we're going 1 left to go 7 down, so you can also go 1 right to go 7 up, things like that. And if that's the case, that means my a value is also 7. If we're talking about getting in this other form, the whole y equals whatever, this would be 7 over x minus 1 plus 2. I know all this because our horizontal asymptotes here, our vertical asymptotes here, and 7 is how far you go up after going over 1. So a lot of different things you can do besides just plotting these points. I bring that up because I can plot points very easily off this. So they give you the graph here, how they approach asymptotes. That's all good and great. Let me give you an alternative version of what we can do here by using, they've done a couple different things. I'm going to talk about using division, specifically long or synthetic division here. Let's talk long division. Divide these two. It's just writing an equivalent version of what we already have, and we'll get 2 as the quotient, 7 as the remainder. That brings us to this equation. 7 is a remainder divided by this, 2 is the quotient there. This graph gets us where we need to go. I can divide 7 by 1 to get 7. That's 7 up right here. Boom. 7 divided by 2. What would be 2? 2 is 3.5 up, which is right there, etc. You can go 7 over to go 1 up. That would be 7 over would be right here to go 1 up, things like that, and you can plot all those points. So I know I'm going kind of slowly on that one, but I will on these graphs as a general thing, just so you have an understanding of what you can do for the points themselves. Let's go on to number 11. Let me actually get some graph paper ready. On number 11, we have y equals 4 over x minus 3. Now this is in that graphing form. Oh, by the way, before I move forward, the domain x can't equal 1, the range y can't equal 2. We're going to talk about those for these other questions as well. But for this one right here, this is in that graphing form, the y equals a over x minus h plus k. There just doesn't happen to be any sort of k associated with this. The vertical asymptote is at x equals 3. The horizontal asymptote is at y equals 0. Again, plus 0 is there. And our a value will be 4. So let me get a dotted line ready for us here. So x equals 3 is this vertical line. Y equals 0 is the x-axis. And we approach these asymptotes here. With an a value of 4, I can divide 4 by 1 from here, 1 away to get 4. 4 divided by 2 gets 2. I want to keep dividing by integers if I can. 4 over 4 is 1. Another decent one would be 4 over 8. That just goes slightly off the graph, but 4 divided by 8 is 1/2. That's a good one to talk about because 4 divided by 1/2 is also 8. So that gets us that point up here. So those are a couple points we can draw a curve with, and then we can divide by -1. 4 over -1 is -4. 4 over -2 is -2. 4 over -4 is -1. 4 over -8 is -1/2. And 8 away from 3 is -5. 4 divided by -1/2 is -8. So those are good points to plot. As we can see, these graphs approach the asymptotes. This is how rational functions tend to roll, baby. Got a couple asymptotes, got a couple approaches, and rather poor looking curve, all told. Right there and right there. Now I do the half arrow thing whenever I approach asymptotes. Whether right or wrong, I do it. So there's the curve. The domain is every x but 3. The range is every y but 0. So those asymptotes are going to reveal also what we get there. X can't equal 3. It can equal anything else. Y can't equal 0. It can equal anything else. We don't have to say the greater thans, less thans, things like that. We're all good. Okay, number 12. Same appearance. Same kind of graphing form as number 11. Only now we have a horizontal asymptote that is not 0. So for this one, your vertical asymptote at x equals -5, given the x plus 5. -5 is what I'd substitute to get 0 for the denominator. Can't divide by 0 once again. Y equals 2 is the horizontal asymptote based off that k being 2. Now a is 1. Not my favorite one of them, because only 1 dividing by 1 gives me an integer. The rest are fractions. 1 divided by 1 is 1. 1 divided by 2 is, well, a half. 1 divided by 3 is a third. That's how far up I'm going from these points. 1 divided by 4 is a quarter. 1 divided by 5 is a fifth, things like that. But I can divide by a half to get 2, divide by a third to get 3. This is how far over I'm going now. Divide by a quarter to get 4, etc., etc. Divide by a fifth to get 5. So this is how it approaches on one side, and then on the other side as well. I might do a copy-paste thing for this so I don't spend too much time on it. You can, of course, pause it or beat me on it, depending on what you do. So there's one of them. The other side would basically, I'll do it here. I don't mind plotting the points. It's actually drawing the curve I have a little trouble with. Divide by -1/2, divide by -1/3, divide by -1/4, things like that. So we approach. So again, a lot of fraction stuff. Not really far out, but I've had problems with the numbers being too big as well. So there's that. The domain, x can't equal -5. The range, y can't equal 2. All right, number 13 is the one I'm going to spend the most time with. It's kind of like what we did with the example problem, so I can talk about this one of two different ways. I'm actually going to begin talking about it in the division form, and then I will confirm that the x-intercept and y-intercept that I find are correct, that the asymptotes that you find can work themselves out as well. Now, I did long division previously right here, so I will show synthetic division this time. Let's divide this out. 4 is your root, and 3 and -2 are your descending coefficients of your top polynomial. Bring the 3 down, multiply by 4, add these together, there's your remainder. So this equation can also be rewritten as f of x equals, now 10 being your remainder is your a value, it still divides by x minus 4 being the remainder, and your quotient is 3, this ends up being your k. So now we're in graphing form as we were previously, and we can use this to now plot points on this graph as we previously were. So let's draw the graph based off this information. Again, you could have used long division as well, and there's also another generic form based off this we can talk about, and I'll get to it. But we do have x equals 4 as our vertical asymptote, y equals 3 as your horizontal asymptote, and then we have an a value of 10. Now 10, it's a little high up when it comes to, by the way, we didn't hit any negatives. If this was a -10, guys, we'd be graphing, for example, right here and right here. But because it's positive, like all the other ones were, we're graphing on these areas here. 10 is unfortunate for some of these, like 10 divided by 1 is 10, and 10 up from 3 is 13. So it's not really truly fittable on the graph. I'll pretend like I plotted it. 10 divided by 2 is 5. And the next good point to really plot is 10 divided by 5, which gives me 2. 3, 4, 5, and 1, 2. And going 10 out is unreachable here, it seems, as well. So I can pretend like I'm getting decent points on the curve here. 10 isn't bad, but you need the window range to fit it. And on this side, we don't get it. On the other side, we will. So I'm going to pretend like I'm approaching the asymptotes there. But let's divide 10 by -1 to get -10, which is down here. I actually fit it. 10 divided by -2 is -5. 10 divided by -5 is -2. So we can get those points, and we can also get this -10. 10 away from 4 is -6, and that's 1 down. So I got a few more points on this one. You can see a little bit more approach of asymptote, on asymptote here. It's kind of a bigger curve in general, right? That's what we're going to see. Okay, so there's the curve. Now, some points are kind of hit almost in a fractional way as well. I don't know if these are perfect or not, but let's see if these x and y intercepts are kind of near what they should have been, because I'm going to get those points for you. We could have also taken this equation and we could have gotten all the information from here as well, or more information from it. We could have gotten the vertical asymptote at x equals 4, given that it's the same one as we have right here, so that's no change. The horizontal asymptote is found by dividing this 3 by this 1. 3 divided by 1 is 3. Sorry, y equals 3 divided by 1, or 3. Now, that was the horizontal asymptote we got right here. Agreed? So we got those two. The intercepts would be found by setting x and y equal to 0. The x-intercept we find by setting y equal to 0, and we solve for the numerator with that. So for x-intercept, we do 3x minus 2 equals 0. So add 2 divided by 3, you get x equals 2/3. 2/3 could be where we cross the x-axis right there. Not the best of points, but it's a point we could have had. The y-intercept we set x equal to 0. We plug in 0 here, they go away, and you get negative 2 over negative 4, which is positive 1/2. And that very well could be this point right here. So those points seem to align. Those are the only points I can find easily, meaning there's really not much calculation to do. Any other numbers, you just have to plug in, right? Plug in 5 and see, we don't have anything at 4. Plug in 5 and see what you get. Plug in 6 and see what you get. And those can get a little heavy in calculation, right? Now you got to do 15 minus 2 over 5 minus 4. Okay, that's 13, and you got to plug y equals 13. It's kind of iffy. That's why I like to do other methods and use these other things. So everything I got here seems to confirm what we got. I got my graph. Domain is x can't equal 4. Range is y can't equal 3. Okay, first two sections are done, and those are the ones, even though 6.2 is different from the next ones because the next ones are algebraic, it seems more connected to rational functions that we see in the next three, which are more so interconnected. 6.3 is on multiplying and dividing rational expressions. Now we do have this big list of what are we doing here. We're dividing this expression by this expression here, two different fractions. Your goal here is to basically, through division, you want to write everything as a single fraction and you want to simplify it. You want to cancel out things on top and bottom that would divide. As this is division, though, it can be rewritten as multiplication provided that you flip the fraction. They flip the x squared minus 4x minus 32 up top and x squared plus 9x on bottom. What they also do is factoring. This is the big goal here. Common factor is 3 up here, 6 down here. This is a quadratic factorization here and common factor of x. From here, they decide to merge these as a single fraction. I tend to not actually do the merging of a single fraction, provided that you know that you can still cancel things on top and bottom wherever they exist in this set. For example, x plus 9s can cancel. X minus 8s can cancel. And 3 over 6 reduces to 1/2. So you're left with 1 times x plus 4 on top, or just x plus 4. And you're left with 2 times x on bottom, or just 2x. So x plus 4 over 2x is the final result. Now, what did they write here? These are exclusions, restrictions. These are values that you can't substitute into here because we couldn't substitute it into here. We couldn't substitute it into here because at one point or another, there were values, quantities in the denominator that when plugging these in, you would get 0, and we can't divide by 0. Now, we can't see them in this set, and that's part of what the textbook talks about. X can't equal 0 even still because substituting 0 into here leads to that. Notice they don't say x can't equal 0 because it's implied. So we only do the ones that got canceled or that flipped from taking the reciprocal when you turn the division into multiplication. So when you see x minus 8 right here, these are gone from this equation because x minus 8 over x minus 8 is 1, and it is 1 for every value of x that's not 8. If x was 8, it would be 0 over 0, and 0 over 0 is not 1. So they're saying, guys, you can't substitute x equals 8 into here because you couldn't originally because you'd be dividing by 0. So you can't do 8. You also can't do negative 9 because of these guys right here. Negative 9 plus 9 is 0, and you'd be dividing by 0 there. You might wonder, Mr. Robinson, why can't we do x can't equal negative 4? Why can't we do that? This is in the numerator. You can divide 0 by numbers, right? Yes, you can. So why can't you be negative 4? Because originally, before the flip, if you notice, this factored form was originally in the denominator. This x squared minus 4x minus 32 was down here. So before, there was a time back when we were indeed dividing by this x plus 4. So at some point, because it was divided, plugging in negative 4 into here would mean dividing by 0, and we're not allowed to do that. So this is part of the included steps because you can't see it in this problem. The only one you can see in this problem is x can't equal 0. We don't list it. We only list the ones we can't see. At least that's what the textbook tends to do. So let's go to numbers 14 to 17. We find the product or the quotient. On number 14, we have 80x to the 4th over y cubed times x times y over 5x squared. Now, before I jump into anything, if you treat these as separate fractions, there's nothing here I can simplify, and here I can divide x by x squared and just get that, so it's a little simpler. If you want to rewrite it all as one fraction, we now have 80x to the 4th y over 5xy cubed. Now, whether you chose to write it as a fraction early on or not, it's up to you. The bottom line is this x to the 4th is dividing by that x, whether you see it here or here, and this y is dividing by this y cubed, whether you see it here or here. So that means there's still more to do. And by the way, 80 is dividing by 5. So 80 divided by 5 is 16. That goes up top. We remove the x down here to remove an x up here. We're still left with 3 of them. And we remove the y up here to remove a y down here. We're still left with 2 of them. So our final result simplified will be 16x cubed over y squared. Now, among these things are the restrictive values. There were x's in the denominator at the time. There aren't anymore. So we have to absolutely state whether x, what restrictions on x there are. X couldn't equal 0 before, so it still can't equal 0 now. Just because we canceled them doesn't mean that that part is not true, because it wasn't, it was true to begin with that we couldn't equal 0, so we still have to hold that truth to be self-evident. Number 15. Not a set of monomials anymore. Now we got to do some factoring. Perhaps basic. We'll see. On number 15, we have x minus 3 over 2x minus 8 times 6x squared minus 96 over x squared minus 9. X minus 3's got to stay as it is. Everything else has some sort of factorization. This factors in 2x minus 4. 2 times x minus 4. This is a common factor of 6, where you get x squared minus 16. I bring that up so I can do this extra factoring alongside of it. We can factor that to x minus 4 times x plus 4. It's a difference of 2 squares. And this is also a difference of 2 squares, which is x minus 3 times x plus 3. Now, I tend to not write an extra step to write them as a single fraction. If you notice from the previous one, I mentioned these are dividing by these are dividing by these, and that's the same thing here. I can divide, for example, these 2x minus 4s. I can divide these 2x minus 3s, and I can divide 6 by 2 to get 3. So ultimately what we have, no need to distribute again, we have 3 times the quantity x plus 4, all divided by x plus 3, and that's a simplified result of this the original expression. Now, in the original expression, there were some x's that were not allowed to be, and we saw them through the factoring and cancellation of. Previously, x couldn't equal 4, so x still is not allowed to equal 4 based on these x minus 4s here. X also couldn't equal 3 based off these ones here. So x can't equal 4 or 3. Those are the two restrictions here. X still can't equal negative 3, but it's implied we can tell by still seeing it here. We can't see these in the simplified version anymore. So you can tell as much as I had distaste for that previously in the textbook, I'm warming up to stating those that way I state it now. Number 16. Ooh, this is a perfect square trinomial. It's a different kind, but it is one. We have a perfect square trinomial up top we're going to factor. We can common factor an x here, among other things. All right. I'm seeing things as they are. Okay, so next problem is also division. Okay. Before we do the flip, let's actually do the factoring. Actually, let's do the flip. Let's do both at the same time. This is a perfect square trinomial. This factors into 4x minus 1 quantity squared. It's 4x minus 1 times 4x minus 1. Hopefully you can recognize why that is, you IM3 folk. If I factor out an x, I get x squared minus 7x plus 12, which that factors to x minus 4 times x minus 3. So I'm trying to do everything out as quickly as I can here. There's a flip here when we multiply by the reciprocal. 15x cubed I can't do much to, so I'm going to leave it like that. On top here, I can factor out a 5x. Well, it's now down below, but I can factor out a 5x, and I'm left with 4x minus 1. So here's my doing. Let's work on some cancellation aspects of this. 15 over 5 is 3. 3 up top. Notice there's an x here and an x here and an x cubed up here. I can remove both x's down here and 2 of the x's up here, and I'm just left with an x. There are 2 4x minus 1s up here. Let's remove one of them with the 1 down here, and I think that's it. So I'm left with 3. If you can still follow your work, I'm left with 3 times 4x minus 1 all over x minus 4 times x minus 3. So I think that's all that remains. Nothing else here cancels. Now, there are some things that we got to be careful of as far as what x isn't allowed to be. No more x's in the denominator where there were before. These x's, yes, but not x factors, which means x can't equal 0 is one of our... Oh, I'm missing this x. Uh-oh, 3x. No, I got to organize my own work. So 3x here. Despite the fact that there's an x in the numerator, x is still not allowed to equal 0 because the ones that went away in the denominator. X can't equal 0. there was a 4x minus 1 that went away. Now, if 4x minus 1 can't equal 0, you add 1 to both sides and you divide both sides by 4. X can't equal 1/4 is among our sets because of this one. X can't equal 1/4. Now, was there anything here? Here's another place where x couldn't equal 0. Remember when pre-flip, this was in the denominator? That's an x there that if it equaled 0 would be a problem. We already listed it right there. Everything else is still in the problem or didn't cancel out, so these are the only two exclusions on it. Okay, let's go to number 17. On number 17, we divide a rational term by a polynomial quantity. So the polynomial quantity is just another way of saying that that thing's being divided by 1. And when you divide by a whole amount of something, then you can also rewrite it as 1 over that number when you multiply. So this one here factors to x minus 8 times x minus 5. This one factors to x minus 5 times x plus 3. This division here is also, once again, multiplication by this reciprocal, 1 over this guy. And this guy factored is x minus 8 times x plus 3. Excuse me. Okay. So the 1 ain't doing much. X minus 8's here, x minus 5's here. You're left with a couple x plus 3's. They don't cancel. They're together in the denominator. Now, when they're together there, generally we wouldn't want to even write that as 1 over x plus 3 times x plus 3. We would do 1 over x plus 3 quantity squared, kind of like that. And that's the way that I'd prefer seeing it personally. So what can't x equal? Based on the canceled x minus 8's, x can't equal 8. The canceled x minus 5's, x can't equal 5. Take a look at the original thing here that was divided. Its denominator was just a 1, so there's no other restrictions to be added in that. So these are the only two restrictions within, outside of course, x can't equal negative 3, but that's implied from that. Give me a second here. Okay. Excuse me. Let me clear my throat here. Okay. All right, section 6.4 is on adding and subtracting rational expressions. Seems easier than multiplying and dividing, but unfortunately it's not, because now you got to seek common denominators and work off that, which requires some multiplication or division sometimes. Okay, or multiplication rather. Find the sum of these two things here. Now they jump right off the bat with showing two unlike denominators, which is good. I don't think any of these have any like denominators, common denominators, so we have to work off that a little bit. So what they do is they work on factoring the bottom. Don't worry about the top, even if factorable. We don't want the top to factor until the very end, if factorable, because we want to combine things up top. On bottom, we want to find the least common denominator, the LCD. We want to find what's different in these. 6x plus 24 factors to 6 times x plus 4. This guy factors to this times this, and if you notice, each of these share an x plus 4. That means you don't need an extra factor of these for each of the denominators to make them common. To make this one common with this one, you got to multiply an extra 6. That's why they multiply 6 over 6 on top and bottom. And over here, this needs that missing x plus 5. That's why you see an x plus 5 multiplied here and here. Now, if you're coming off this review having seen my 6.5 thing on solving rational equations, don't start canceling out denominators once you find a common denominator. That was very, very specifically for equations when I'm technically multiplying both sides by the least common denominator so that it goes away. This is an expression. You can't say, oh, I have 10 divided by 2. Let's just take out the over 2 and just make it 10. No, 10 divided by 2 is still 5. It's still 10. You can't change it. So this denominator will remain on the problem the entirety of the time. These are back to expressions. Anyway, case in point, x distributes with x plus 5, we get this. 6 distributes with x plus 2, you get this, and they do distribute. And then you combine like terms up top, because now you have a common denominator. You leave the denominator the same, you don't add them. You know what I mean? You keep them the same, and you add the top, and then there you have it. There's your result. Now, there were no restrictions because nothing canceled out in the process. That being said, if this numerator, x squared plus 11x plus 12, could factor, you would attempt to. And let's say there was an x plus 4 inside there that factored, you would cancel them out, and then you'd have something even further simplified. And x equals negative 4 would be a restriction. But there's nothing there, so we leave it. All right, let's jump to number 18. We have 5 over, and this is already factored here, 6 times x plus 3 equals, or excuse me, plus x plus 4 over 2x Our goal of finding the sum or difference is writing this as a single fraction, which means getting a common denominator. If you notice here, nothing's really the same. There's sort of something the same, though. This has a 6, this has a 2. So I don't need to multiply by a full 6 here to match. I just need to multiply by a 3 to match here on top and bottom. But I also need to multiply by this x plus 3 quantity. That is also missing. So 3 times x plus 3. And the 6 don't need no changes. Once I multiply this thing by 3, I will have brought it up to 6. So that's all good. But this is missing an extra x factor here on top and bottom. So now they'll have a common denominator of 2 times 3 times x plus 3, or 6x times x plus 3. That's on bottom, as we now have a top of 5 times x plus, here's where you might want to do a little extra work on the side. 3 times x plus 3 is also 3x plus 9. And we need to multiply x plus 4 with 3x plus 9, which is 3x squared plus 12x plus 9x plus 36. So getting a little more work done there. Now we can combine like terms. I'll write 3x squared first, and then 26x and 36. Is there a possibility that this is factorable? Yes, there's a possibility this is factorable. Is it? I have no idea. I forgot what I was going to look for. I was going to say that if, I was going to find another problem. Oh, it's right here. If this thing factored again on top, then you could cancel it with top and bottom there. This one here, 3x and x. 36 has a couple things. The only problem with 36 is most numbers multiply with the 3. I can try 4 and 9. You get 27 plus 4 is 31. That's not 26. You can do 1 and 36 doesn't work. 2 and 18. 2 and 18 is too big. I don't think this one's factorable, so I'm going to go ahead and leave it like that. You know, none of the other ones we found actually were factorable, unfortunately. I like to try and make problems that are with those, and this one's not. All right, number 19. Also an addition problem. We got to deal with subtraction here in a moment. 5x over x plus 8 plus 4x minus 9 over x squared plus 5x minus 24. All right, before we begin this one, let's start by factoring this denominator here, because nothing else can really factor, right? So down here, this factors to x plus 8 times x minus 3. It's kind of a godsend that there's an x plus 8 there, because this also has that x plus 8. This is missing the x minus 3 that the other guys got. So we're going to multiply top and bottom like that, and then we have a common denominator. So now that we have a common denominator, I can distribute the 5x into here. And then I'm adding this 4x with this 9, negative 9. And then on bottom is that one common denominator of x plus 8 times x minus 3. When I combine things, I have 5x squared minus 11x minus 9 over this. And it's once again a question of, is the top factorable? I'm trying in my head. It could actually get close if I could, oh wait, yeah, I could, listen, this is wrong, but if this was minus 3 plus 3, you know what we'd get? We get 5x squared minus 12x minus 9. That gets really close, but that's not quite the same thing. So because of that, it doesn't work. That would have been nice if they did do, you know what, that would have been nice if they did do something like that there. If they turned this to 4x minus 10, they would have gotten the x minus 3s to cancel. That would have been a better problem, and yet they refrained from making a better problem. How dare they? That would have been really cool to do. Book, change this to a minus 10, make a cool problem out of it. I promise you it would be cool. All right, hopefully they can do that in the future. All right, number 20. I'm improving their book. Number 20. We have x plus 2 over x squared plus 4x plus 3 minus 5x over x squared minus 9. Now the minus doesn't do anything different than the plus when it comes to seeking common denominator. We will have to be careful of one thing with subtraction once we do seek that, though. So just be ready for that. All right, start factoring some bottoms. This is x plus 3 times x plus 1. This guy is x minus 3 times x plus 3. They both share the x plus 3. This one's got an x minus 3 that this one don't. This one's got an x plus 1 that that one don't. So this needs a couple x plus 1s on top and bottom. This needs a couple x minus 3s on top and bottom. And we're going to have to work this thing out through, FOIL distribution, things like that. And there is a minus in between. I need to keep reminding you of that minus. Get that ready. So for this problem, we do have a common denominator now of those three factors: x minus 3, x plus 3, and x plus 1. On top, x plus 2 times x minus 3 distributes to x squared minus x minus 6. Now this minus, this is where it gets a little bit tricky because 5x may distribute into here and become 5x squared plus 5. I got it. But this does not become minus 5x squared plus 5 like that because this is really negative 5 times those two things. So it's actually minus 5x squared minus 5. We distribute the negative into everything that goes on there. Whether you call it a negative 5x or call this a 5x and then distribute the negative into it, it's negative 5x squared minus 5x that we have here as we continue forward. But that's the one part about subtraction that you really got to be careful with, and I'll remind you each time if I can. X squared minus 5x squared is negative 4x squared. Negative x minus 5x is negative 6x, and you got a minus 6. Now, besides the common factor of a 2 up top that I see, I also see a negative I can factor out, and it's in your best interest to factor out negatives, leading negatives as often as you can. So I got 2x squared plus 3x plus 3. Not that I believe it's factorable, because it doesn't appear to be, but you do that factorization to try and see if there is any factorization that you can possibly do on that. It doesn't appear so. So we move forward. We're done. All right, rewrite the function in the form g of x equals a over x minus h plus k. Graph the function. Describe the graph of g as a transformation of the graph of f of x equals a over x. So we did these problems in this section. It's back to graphs again, which is a little bit bizarro when you're like, wait, we just did the graphs. We get to do more. Now, some of these graphs got a little weird and a little far for me at the time. Now, you just saw a problem, where we did do a rewrite of this in the other form, but we did it using division. Here in this section, this is the addition and subtraction section. If you're wondering how this has to do with what we're doing, we're going to solve this via what's called inspection, or convert it via inspection. Inspection is a way of rewriting the top and splitting this into two different fractions, so we can cancel the x minus 3 on top and bottom of one of the fractions and get it in this form where we get that k value. The way to do it is to turn the coefficient that has the x into it into a common factor that will have an x minus 3 on here, as in turn it into 5 times x minus 3. But this isn't plus 1 anymore, because 5 times x minus 3 is 5x minus 15. We get 5x minus 15, and 5x minus 15 plus 1 ain't 1, but plus 16 gives us 1, and that's what we're dealing with there. So we want to distribute an x minus 3 in with the 5. So now this is another way of saying 5x plus 1. The difference is when I factor 5 from here, I get x minus 3. And not that things can cancel right now because we have an extra term of 16, but when we split this as two different fractions, this is 5 times x minus 3 over x minus 3 plus 16 over x minus 3. Common denominators can also be split as well as joined, right? So this allows us to now divide these x minus 3's together, and now it has a completely different version of this equation. It's the same equation. I'm going to write the 16 over x minus 3 first, and then plus 5 after, and boom, we have a rewrite of that. Is this preferred to me over division? No. This is a lot longer. But is it something that works, and is it something that uses addition and subtraction and all that? Absolutely, yeah. Okay, so we are going to graph this. Now, this isn't terrible. The 16 won't guarantee us getting every point that I would have liked, but x equals 3 and y equals 5 are our two asymptotes. Hopefully now we kind of know how that thing works. 16 can divide by a lot of numbers, though. It can divide by 1 to get 16. That's too high up. It can divide by 2 to get 8. Probably still too high up. 6, 7, 8, probably up there. I can divide it by 4 to get 4. Over 4, up 4. I guess that's kind of it, right? Divided by 8 again, I get 11, and then 16 divided by 8 is 2. So I don't get very many points on this side. I think it's the other side you're going to see a lot more of our graph. But there's a little bit there. It's just an idea of it. Let's go ahead and go the other side. 16 divided by negative 1 is negative 16. Doesn't exactly fit, but it kind of does. And if it kind of does, I'm going to kind of use it. 16 divided by negative 2 is negative 8. Divided by negative 4 is negative 4. Divided by negative 8 is negative 2. And divided by negative 16 also doesn't really fit, but is negative 1. About way over there. So getting an idea of the curve so you can see just it approaches the asymptote even still. It doesn't just hug it immediately once I run out of points to plot. But it gets closer and closer there. Now what they want to do is compare this to the graph f of x equals 16 over x. Basically keep the same a value and compare the two. All there is, and you're going to see this in every problem here, is just a translation. The graph of g is a translation of f. 3 units right and 5 units up from f. So there is the first of these problems. Now these will only go as fast as I can handle the graphs. Now that we've done some graphs, I'm going to go relatively quickly on that portion. That being said, I'll probably speed up a little bit more on the inspection portion now. Number 22 says g of x equals 4x plus 2 over x plus 7. This time here, once again, let's distribute the x plus 7 into 4. So we now have 4 as a common factor of these two terms, so we can cancel out some x plus 7s later. But we do need to rewrite 2 as 28 minus 26. This is going to allow us to do exactly that. Now I am going to split this up and do the common factor. So common factor of 4 right here gives us x plus 7 as we divide by x plus 7 here. And then the negative 26 here divides by x plus 7. As these x plus 7s go away, the best rewrite of this equation is g of x equals negative 26 over x plus 7, and then plus 4. There's our a over x minus h plus k. Now this has a couple different things going with it. For one, the a value is negative. For another, this a value is pretty big. Pretty big. I was going to say relatively large. So this is one where I get a little iffy about what to choose to do. I could scale by 2s. Let's scale by 2s on this one, just to kind of get a bigger picture of what we got. So this is 10 and 20. Now our x, our vertical asymptote, is at x equals negative 7, which is halfway between negative 6 and negative 8, so about right there. And then y equals 4 is now right here because we're scaling by 2s. Now the 26 being negative means when we go right, we go down. If I go right 1, and remember 1 goes from negative 7 to negative 6 like that, then I go down 26. I go down from 4 to negative 22. Negative 22 is not quite on the graph, but it's really close. It's about right there. So I will fit it, and it's something I can only fit now and I couldn't have fit before. 26 doesn't divide by too many numbers. It divides by 2, 1, 2, 13, and 26. So I divide it by 2 and get 13. 2 over is right here. 13 down from 4 is negative 9. So I'm going to be about right there. And then I can go 13 over from negative 7 to be positive 6. 2, 4, 6. And 2 down from 4 is 2. And then I can go 26 over from negative 7 to be 19. Like right here. And I can go 1 down like that. So those are a couple points that I can plot on this side of it. A lot more than I can plot on the other side. The other side I'm only going to be able to do the 13 and the 2. Things like that. But this still works as my curve for this thing. Now, if there are other points that we could kind of confirm along the way, something I didn't really do off the previous problem just because the graph was a little bit easier to look at. This one we could talk about x and y intercepts. Are they 1 and negative 1? I don't know if they're actually 1 and negative 1. But you can check them by plugging numbers into here, because this is my curve perfect. My x-intercept, when you set the top equal to 0, you subtract 2 and divide by 4, you actually get negative 1/2. So it looks like my curve ain't great for that. I'm going to try and fix it based off that. My y-intercept would actually be 2/7. You set x equals 0 and you get 2/7. So let's try and redraw that curve portion. This is the price I pay for not having more points here. But the x-intercept would be negative 1/2, which is actually about right there. It's a quarter of the way between 0 and negative 2. And then y equals 2/7 is probably even like smaller as far as the thing goes. So about right there. So our curve should really be probably hitting more of that before bringing itself down like this here. Probably messed up that portion though. On this side, I probably won't do reflections of those, but I will do my going left 2 to go up 13. 13 up from 4 is 17, so 12, 14, 16, 17. And 13 over from negative 7 is negative 20 to go up 2, boom, like that. So those are really the only 2 points I'm going to be able to plot on this side, personally. Make it look all good and stuff. And curve its way into and out of there. Okay, those are our 2 hyperbola branches. Not domain. Transformations. The graph of G is a translation 7 units left and 4 units up from f. F of x would have been negative 26 over x. Number 23 says g of x equals 9x minus 10 over x minus 1. Okay, more of the same there. I'm trying to decide, and I see a word problem down below, but it would be the first of our word problems. I'm trying to decide what other kinds of problems we should have seen more of. We've seen 10 inverse variation problems. These three problems I would have limited to, just a couple, if that, because we did some graphs. It's good to get some more graphs in. I just hope these numbers here are good. That's all. I would have dealt with some more word problems probably, even in the inverse variation set. All right, 9 times x minus 1 is 9x minus 9. So that distributes into that, and then you subtract another one to get negative 10. So that doesn't fall too far off in general when we're looking at that. This divides by x minus 1 still. Now we factor 9 from here to get the x minus 1, split off these x minus 1s with 2 different fractions here, like that. X minus 1s go away. Okay, this graph thing ain't too bad. negative 1 over x minus 1, and then plus 9 ends up being our equation here. So with that equation, we can graph the horizontal asymptotes rather high up. You know what we also didn't have? It doesn't matter. We didn't have a horizontal asymptote that was negative. I seem to rarely get them, actually. I think I remember complaining about that, pointing that out when we did the sections as well. But this has a horizontal asymptote at y equals 9 and a vertical asymptote at x equals 1. I don't know. I think it takes very little to just do one change here and there. Anyway, negative 1 is your a value. So negative 1 divided by 1 is here. And, you get those fractions as we did before. Divided by 2 to get a half, divided by 3 to get a third, 4 to get a quarter, 5 to get a fifth. Divide by 1/2 to get 2. We go 2 down. A third to get 3, a quarter to get 4, and a fifth to get 5. So there's that slow approach. If I went for x and y intercept on this thing, well, let me tell you, the y-intercept is going to be fine. The x-intercept is going to be very, 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 very slim. How slim will it be? Well, consider that we would go over 1/9 to go down 9. So it would be 1 and 1/9. It would be 10/9. And that makes sense with this problem. You add 10 divided by 9, you get 10/9. So kind of a weird x-intercept, so I'm not going to bother with it. The y-intercept will be kind of normal, though. You divide by negative 1, you get positive 1. The y-intercept must be 10. Let's see. Plug in 0 for x right here. You get negative 10 over negative 1, which is positive 10. So that makes sense. Divide by negative 2 and negative 3 and negative 4, and it stretches closer and closer. This would go higher up here, though we can't see it. So here's the other portion of the rational function. Not the worst graph, but we don't get that side quite as much, and everything is a fraction besides the 1. At least it's quick enough. Now, this is a transformation of negative 1 over x. We go 1 right and 9 up. Like that. And there we have it. All right, that's using inspection to get those rewrites. Again, longer synthetic division can get us the same values. Number 24 is a word problem, and it says, let f be the focal length of a thin camera lens, p be the distance between the lens and an object being photographed, and q be the distance between the lens and the film. For the photograph to be in focus, the variables should satisfy the lens equation to the right, and that's right here. Simplify the complex fraction. It's not really a word problem. They just say simplify it, but this is, and that's another one that we didn't get to run into yet until now. This is a complex fraction. A complex fraction means it has fractions within fractions. Now, my preferred method of going about this is, this one is good as it is, right? In terms of rewriting this, this would be 1 divided by whatever we have on bottom here. 1 divided by this guy. And this guy here, we can get a common denominator by multiplying p over p here and q over q here. So we get p times q on bottom. And on top, we have q plus p, or I can write p plus q, like that. Now, this 1 ain't doing very much other than existing, but multiplying anything by 1, because we're going to change this to multiplication, we multiply by the reciprocal, p times q over p plus q, like so. So therefore, f is p times q over p plus q. Now, given the original restrictions here, remember we can never be dividing by 0. That means this p and this q could never be 0, whether it existed at this time or at this time right here. So I probably need to mention p can't equal 0, q can't equal 0, and then we're all good with the simplification. So there's our final result of that one. Not really a word problem. They just kind of gave you information. It's cool information on cameras, but didn't really create the model, you know, didn't really interpret what things meant. So it's a little different. All right, before we hit the final sets of number 25 to 31, we're going to talk about solving rational equations as a whole. And I know I made a big stink about all the different methods that you could do at the time with these, so I'm going to limit myself a little bit. I don't write it exactly as the book does, but I still have the same idea as the book, for the most part. Now, this problem here has not a common denominator among all three. It does have a common denominator for these two, and I do want to let you know about that a little bit. Let me go down here for a second. You see these first couple problems right here? These are proportions. These proportions we can cross multiply. You can cross multiply because there's one fraction on each side of these equations. If there's one fraction on each side, anywhere you have a common denominator, it might be wise for you to just, bring this whole term over and merge it so you have a proportion. I'm not going to do it for this problem. They didn't do it for this problem, but I'm letting you know that you can do that. So what did they do? They found the least common denominator. These x plus 3s are missing in x minus 4, and this x minus 4 is missing in x plus 3. So if you got a common denominator, you'd multiply this top and bottom by x plus 3, these top and bottoms by x minus 4. They said multiply everything by x plus 3 times x minus 4, not on top and bottom, just on top, because then certain things would cancel. This would lose the x plus 3 on bottom and have that x minus 4. This would also lose the x plus 3. This would lose the x minus 4, and you see what remains there. I do it kind of differently where I do get the common denominator, but then I ignore the common denominator because it's the same thing. You're dividing by the same thing everywhere. Now, the one thing we're going to have to be very careful of, though, is that as we get rid of denominators and we have no more fractions and we have this, we have now created a brand new type of equation, in this case, actually a quadratic. The original equation was rational. Rational equations have division by 0 things we have to be careful of. For example, x can't equal negative 3 and x can't equal positive 4. Keep that in mind when we solve for x. We don't need to write these two things. We just need to know if we get either of these as solutions that we need to list them as extraneous. So let's continue solving here. They do this multiplication of these, and if you get bothered, if you're confused by that still, we have some more problems to try with it. We're going to distribute negative 4 into these two, FOIL this out and distribute x there, combine like terms, set everything equal to 0, and divide everything by 2. You got a basic quadratic that you can solve by factoring, and zero product property. X equals negative 3 and x equals 2 are your solutions. Now they do a double check down here. I am not going to personally do a double check and see if left side equals right side. I'm just going to see if any of these values are part of my extraneous solution set. Negative 3 is among them. Negative 3 is extraneous because that would lead to division by 0 in the original equation. 2 is fine. And if 2 is fine as far as extraneity goes, or non-extraneity, then 2 is fine as far as getting the correct number. So x equals 2 is the only solution to this thing. The apparent solution here is extraneous. The only solution is this guy. So let's go and do these for these problems here. On number 25, you actually have a proportion, though, and I brought that up previously. So I'm simply going to cross multiply on a question like this. Makes it a little bit easier to work off of. So here we can cross multiply straight up. And we got 5 times x plus 2 equals 7x. And I don't believe cross multiplication is really a new thing for you guys. It's just kind of showing that it exists in this set. I'm doing this kind of in my head right now. X equals 5. Cross multiplication, according to the book, it's a new phrase. But, you might have learned these ideas before. You might have been taught it before or whatever. The book might have lent you to know what this stuff is. Now, 5 works. 0 and negative 2 would not have worked. 5 is a fine answer. I'm not going to double check it. It should be fine. But that is the solution. Now, number 26 is also a proportion, which I can cross multiply with. However, I'm trying to think if that's what I want to do here. See, this x squared minus 4 can also factor to x plus 2 times x minus 2. I'm going to show two different ways to do this problem, okay? This one to me is the hybrid of all the other problems that are lent here. There are a lot of things I can do on 27 as well. I feel like I want to do a little, you can do this or that kinds of things. One version is cross multiply, right? We can cross multiply, and this 8x times x minus 1, by the way, is 8x minus 8. I say that because I'm going to have to start, doing distribution here. And this is 4 times, I have a lot of ways I can do this problem. X squared minus 4. Like, for instance, I could have divided the 4 with the 8. Man, there are a lot of things I could have done. Oh, well, I'll go big. Maybe this is how you would have seen it, so I'll go big with you. So this is 8x squared plus 16x minus 8x minus 16. And this is 4x squared minus 16. If I add the 16s together, they cancel. If I subtract 4x squared over here, I get 4x squared plus 8x equals 0. I could factor out a 4x here, and you get x plus 2 equals 0. And you get either x equals 0 or x equals negative 2. Now, when you look at the original equation here, negative 2, either on this part or this part, by factoring or whatever, would have led to an extraneous solution. So negative 2 actually does not work. 0 is fine because 0 plus 2 is not 0, and neither is 0 squared minus 4. So x equals 0 is good. That's your only solution. That's one way to do the problem. Another way to do the problem based off like common denominator stuff is, for instance, I could have factored x squared minus 4 into x minus 2 times x plus 2. And then here, this one has the x plus 2, but it's missing that x minus 2. So I can multiply top and bottom by x minus 2, and this is where I do something slightly different from the book. They would say multiply both sides by x minus 2 times x plus 2. I seek the common denominator, so I see all that's needed on top. So now the denominators can be ignored. This is true for equations, not for expressions. If I now multiply both sides by x minus 2 times x plus 2, they go away. So now I only have an equation that says, if I distribute, 8x minus 8 equals, and 4x minus 8. If I subtract 4x from both sides and add 8 to both sides, I get 4x equals 0 and x equals 0. Notice here, the extraneous solution didn't even surface. It didn't even pop up, and 0 is the only solution that's had, so cool, it still works out. So no matter what, we are getting x equals 0. It seems that either method works out for us. I don't know which one you prefer. This one actually looks a little faster. Just depends on what you want to get going with it. All right, let's move to number 27, where I do have, again, two different ways that I want to talk about going about this problem. I have 2 times x plus 7 over x plus 4 minus 2, and that's over 1. I want to remind you of how that can work later, equals 2x plus 20 over 2x plus 8. Now, first of all, you can't just cancel out these 2x's. No siree. That's not something you can do. But I do see something here, and I kind of want to explore it and use it. 2 is a common factor on top and bottom of that beginning portion there, and I don't see a reason why I need to leave it there, because otherwise you got to multiply these by 2 when they don't really need to. Normally we don't talk about factoring the top. However, because it's a direct common factor with this guy right here, these 2's really are not needed. You're just left with x plus 10 over x plus 4. So for the sake of this problem and every version of this that I'm going to have, I'm just going to rewrite this as x plus 10 over x plus 4. What's really nice about this now is that these are the same. There's nothing else I need from that. Just this one I need a little more something with. So I got to multiply this one by x plus 4 on top and bottom, and then boom, I have a common denominator. If I have a common denominator, I can then ignore it. So I'm going to ignore the denominator now, and I'm going to rewrite everything up here on top with distribution. 2x plus 14, be careful, this is subtraction, negative 2 times x, negative 2 times 4, and this equals x plus 10. Now that everything compares evenly, we can do that. 2x minus 2x is gone, 14 minus 8 is 6, and subtract 10 from both sides, you get x equals negative 4. Now, we got to double check this negative 4 with our original equation, and here you can tell whether here or there, whatever, you divide by 0. So that is an extraneous solution. That means if that solution is gone and no other solution exists, our answer is no solution. And that's literally it. It's no solution. Okay. Now, that's one way of doing the problem. Let me actually do that all kind of like in blue, because I want to do it in a different way here. Take the same, oh, hold on. Give me 1 second. let me just turn this into blue because I want to still take the same equation. So take this equation otherwise. Let's do a slightly different version. This one for me will not be preferred only because I got to move two sets of things to other sides. Because these are common denominators, I could merge them as a single fraction on its own side of the equation and move this 2 over 1 to the other side. So if I add 2 over 1 over here, and remember, that's the same thing as 2. It's up to you, 2 over 1 and 2. I can subtract this x plus 10 over, where I have the 2x plus 14. Let's subtract x plus 10, like that, and combine it with these common denominators. Subtract the x, subtract the 10, right? So now this is x plus 4 over x plus 4 equals 2. This is an interesting version of the problem to speak about, actually. X plus 4 over x plus 4, do they cancel out? No, but they divide and become 1. So x plus 4 over x plus 4 is 1. You get an equation that says 1 equals 2. That's kind of nice to show this because this is a version that shows there is no solution for x that makes the left side equal the right side. Did I do anything wrong? No. This is another way of stating when variables cancel and left side doesn't equal the right side, you actually have no solution. So I'm going to just bold that up and say, hey guys, we still get that answer right there. So no matter what we do, we get it. And that's a nice way to kind of emphasize that from that bottom part up here. Okay, so there's number 27. Now that I felt like we got to do a lot on those problems. I would have liked to have more of those problems, to be honest. Probably less inverse variation. Determine whether the inverse of f is a function, then find the inverse. They didn't say graph, so graphing is not what we're going to be doing. I'm going to find the inverse first, and I'll tell you whether or not it's an inverse. Here we have y, and we swap x and y to take the inverse, and we got to solve for y all over again to then find the inverse. We can multiply both sides here by y plus 6. Without distributing that x, we'll divide both sides by x as well. So these go away, these go away. You're now left with basically switching places. Y plus 6 equals 3 over x. And we can subtract 6 from both sides. We'll get y equals. I'm going to write in inverse notation because this will be my final inverse once y is by itself. 3 over x minus 6. This is a function. It's a function because substituting any value for x, you can't plug in 0, but that's fine. Substituting any value for x will only get one y value out. It's when we hit plus or minuses that we will have something different. And you only hit plus or minuses when we do like square roots of both sides or fourth roots of both sides, some sort of even roots of both sides. That's not the case in these problems. So I imagine every of these will have a function whose inverse is a function. Number 10 is a lot more of the same. There's not really much I can say that's going to be different on this one. Turn f of x into y because they're the same. Swap x and y because we are taking the inverse. And solve for y all over again. They can swap places, y minus 7 and x. That is not a magic step. That is a math step. Same with like cross multiplication. There's actually something to it. And add 7 to both sides. We get 10 over x plus 7. Not to graph it, but the inverse would pass the vertical line test, so it is indeed a function. And then number 30, slight variation of the problem. Number 30, we have f of x equals 1 over x plus 8. Turn this into y. Swap x and y, taking the inverse. And now let's solve for y. Before, you can't switch places here to start with because this would be multiplying both sides by y, which means this would have to multiply by y, and we ain't doing that right now. Subtract 8 first, make this a single quantity, and now when you multiply by y, it's to the whole quantity, divide by x minus 8 to the whole quantity. So in switching sides, you get y equals 1 over x minus 8, which is also the answer. So the inverse of this function is 1 over x minus 8. There you have it. This is also a function. So none of these weren't functions. We all good. They all the same. Yeah, all finished. The last question of our review, this has gone for a little while. The last question of our review is number 31. It is a word problem. We were lacking in them a little bit. At a bowling alley, shoe rentals cost $3 and each game costs $4. The average cost C in dollars of bowling end games is given by this model. So they are nice enough to give us the model. We could have come up with that as well. Maybe when it comes to the chapter test, they're going to do a lot more where we come up with models. So the top is basically how much you're going to spend on bowling in general. Divide by the number of games and you get the average cost for each game. Find how many games you must bowl for the average cost to fall to $4.75 by either solving the equation or using the inverse of a function. So how many games is n? So your part A version of this is you substitute 4.75 in for C, average cost, to then solve for n. And it's your choice how to do this, but you need to make sure you know what you're doing with this. I'd have to multiply both sides by n to begin with here. Don't try and get tricky and cancel n's out or something like that. So we got 4.75n equals 4n plus 3. I can now subtract 4n from both sides, 0.57n equals 3, and divide both sides by 0.75. Now 300 divided by 75, I believe, is 4. So 3 divided by 0.75 should also be 4. So this is 4 games. You can play 4 games to average $4.75 per game. And the average changes per game because that upfront cost makes this not a direct variation situation. Now that's part A. Part B says get n by itself otherwise and then do your substitution for this. Now, there are 2 different ways you can do this. One is the way the textbook would probably be representing, which is fine, which is splitting this n up. Remember, common denominator, so you can then divide there. So now you have c equals 3 over n plus 4. That didn't get n by itself, but it got us to a single n. If I subtract 4 from both sides and then switch up the n and the c minus 4 like those other equations, you would get n equals 3 over c minus 4. And this is fine. This is actually a pretty good equation to work off. Now, based off this, that's not the answer, but based off this equation, we can then substitute 4.75 for c. So you get n equals 3 over 4.75 minus 4, or n is 3 over 0.75. We kind of saw that before, and that would be 4 games. 4 games. So that's one way of doing it there, getting n by itself, and by taking that inverse and getting n by itself. Alternatively, what we could do is this. It's a little bit trickier, and it actually follows a little bit more of this model of getting the n's on one side of the equation, even though here they would combine. In our problem, they won't, but you'll see what I'm going to do here. This is the next version is the one I personally prefer, but let's see if you do. I'm going to multiply both sides by n to begin with, just like that previous problem had. We'll have c times n equals 4 times n plus 3. I'm going to subtract 4n from both sides to get all n's on one side of the equation. Even though they don't combine, n is a common factor. And you can factor it out there. Now we can divide both sides by c minus 4, and you get n equals 3 over c minus 4. So take a look. That actually matches with this one. So they are the same exact thing. I don't know which one you prefer. This one, you had to split this thing up and see the cancellation, do some stuff. This one, you needed a common factor and seek that out. So either way actually works. You still get to that same equation in which you do your substitution and solve. Now, which do I prefer? Finding the inverse and substituting, or substituting straight up and solving? I think I prefer this one more for a problem that only has one substitution to do. If I had multiple to do, I'd make a whole equation out of this. I'd put it in the graphing calculator and I'd plug them into a table. So we can literally use this if you wanted to. And I know I'm done. I'm done, by the way. But if you wanted to here, we could have literally taken this thing, made n equals 3 over c minus 4, like this. And then boom, you have not only a whole graph, I don't care about the graph, but you can plug in anything for n you want except 4. You can't do, you can't spend, remember, this isn't number of games on Y, this is number of dollars. You can't spend $4 apparently on average. You can't average $4. You also can't have negative dollars spent here as well. But this is the number of games you could play. No, excuse me. This is the number of dollars you can spend. 5, 6, 7, 8, etc. And this is the number of games you can play. Problem is you're hitting decimals all over the place because you have to hit certain cents amounts to work it out. So maybe this isn't the perfect example of what to talk about. But you could also find certain things there to do it. Basically, $5 gets you 3 games. $7 gets you 1 game. For those averages, $7 averages, things like that. $7 per game average. That's how this worked. It was a per average, on average thing. All right, guys, that was the last question there. So that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. We have the chapter test and cumulative assessment coming up here afterward. And I'm actually hoping for more word problems, more variation in problems than what we had here. All right, guys, take care. I'm going to see you in the next one.